Hi, and welcome to the third video in the series to understand the atomic structure. Today we're going to look at Bohr's atomic model. Well, that doesn't right. Right. So now, we saw that with the Rutherford model, the electron, if it is moving in a circular orbit around the nucleus, is expected to emit radiation and sort of collapse into the center of the atom, which is the nucleus, which is positively charged. Now, Bohr solved that problem kind of just by saying that electrons revolve in fixed orbits around the nucleus, and when they're in these fixed orbits, they don't continuously emit radiation. So in a sense, he said that we were kind of wrong, but the key point being that he said they revolve in fixed orbits. So if you have a positive center and you have a first orbit, second orbit, the third orbit, he said that these orbits are fixed. So that means that you cannot have any orbit that you would like somewhere in between, for example, and the electrons only exist in these orbits. So they are restricted to these sort of circular paths. And these orbits are also known as shells. Now, what does this orbit tell you about the electron? So, if you can see, this orbit here is quite close to the nucleus compared to this orbit here. Now, what does that mean? That means that the particle that's closer over here is going to experience a different attractive force. So if two objects are close together, two charges are close together, the force of attraction is going to be larger than if they're farther apart. There are ways to test this, but the best way would just be to look at the equation, which states that the Coulombic attraction between two charges, Q1 and Q2, is given by this formula. So that's the charge 1, that's the charge 2, that's a constant, and that R is separation between them. So that means if the charges are really far apart, this part's going to get really big, and if the denominator of a fraction gets really big, the whole value gets really small. So the farther apart they are, the less interaction they have. So if you move these charges really far apart, like to infinity, they're not actually going to pull each other. Right? And that intuitively makes sense, whereas if they're relatively close to each other, they're going to pull each other. So over here, this shell has an energy associated with it. And this shell has a different energy associated with it. So these shells can also be thought of as energy levels, simply because the energy is given by this equation, and this shell is at has a certain radius, which means it's a certain distance away from the positive center, and this electron's negative. Right. So if shells are energy levels, what Bohr is actually saying is that electrons stay in fixed energy levels where they don't emit radiation. So he's saying that the electron is restricted to certain specific energy levels and cannot exist in between. So if the electron does exist in between, it can have any energy it wants, but he's saying that it cannot, that they're only restricted to this position or this position or this position, which means they have fixed energy levels. And this is also known as quantization. It's a fancy word, but it really just means that it's fixed and it's not continuous. Quantization of energy, which we will look at later on, so you don't need to worry about that too much. Now, if electrons stay in fixed energy levels, there must be something that might happen when an electron tries to move, right? Do you think it's possible for an electron to jump from here, from one fixed energy level to another fixed energy level? And in fact, it is actually possible for electrons to jump between energy levels, so they don't actually stop here. If it's in, let's say, shell 1, which is also known as K, by the way, just some nomenclature. The shells are also labeled by letters K, L, M, N, or 1, 2, 3, 4. So electrons can jump between shells, or between energy levels. So an electron in shell K can go to shell L. And an electron in shell L can go to an electron can jump to shell M. Can also come back down like that. From an electron in shell L can come to shell K. An electron in shell M can come to shell K. And these were all based on observed phenomena called spectral lines. So they saw the existence of these lines called spectral lines, and they explained it by considering the fact that electrons jump from one shell to another. And the way they explained this was by associating this change by jumping from one energy level of E1 to E2, the change in energy is what is emitted radiation. So he said that electrons don't continuously emit radiation, but if an electron jumps from one shell to another shell, it emits the sort of gap between the energies of the shells. And this emitted radiation was observed in the form of something known as spectral lines. So they observed spectral lines. They thought, okay, what can cause these spectral lines? And Bohr explained it by considering electrons jumping from one shell to another. Okay, so in the next video, we're actually going to delve a bit deeper into spectral lines for hydrogen, for the hydrogen atom, and look at the Rydberg.